Understanding process management and operating systems is key to this mystery. Let's dive into the intricate world of processes and threads. A process is a job to be executed, which can be a user program or a system process. Threads are lightweight processes sharing the same memory. They can be user level or kernel level. Together, they form the backbone of multitasking. This chapter explores their roles and interactions. Processes move through states: ready, wait, running, and terminated. Each process has unique attributes like process ID and CPU registers. The process control block holds these attributes. It's vital for resuming execution after interruptions. Understanding this helps in grasping process flow. Operating systems manage processes through creation, scheduling, execution, and termination. Each process is tracked using a process control block to manage its state and resources. Context switching enables multitasking by switching between processes, while mode switching ensures system protection by separating user and kernel operations. Scheduling algorithms like round-robin, priority scheduling, and shortest job next improve CPU efficiency and responsiveness. Concurrency and inter-process communication, IPC, allow processes to run simultaneously and share data safely using tools like semaphores, message passing, and shared memory. This chapter explores these essential functions that ensure smooth, efficient process management. Process scheduling determines which process runs next and for how long. Preemptive scheduling allows forced switches like round-robin. Non-preemptive scheduling lets processes run to completion. Modern systems use multi-level feedback queues. This ensures responsiveness and fairness. Processes are created using techniques like forking in Unix-like systems. Exec system calls replace current process images. Termination can occur through exit calls or external commands. This chapter covers these critical lifecycle stages. Understanding them is essential for process management. Context switching involves saving the state of a running process and loading the state of the next one. This allows the CPU to switch between tasks in a multitasking environment. Key elements include saving and restoring CPU registers, program counters, and memory mappings to ensure processes resume correctly. The kernel handles these transitions smoothly, ensuring minimal disruption during execution. Minimizing context switches is crucial, as each switch consumes CPU time and resources. Reducing unnecessary switches improves system efficiency and ensures effective process management. Processes often need to share data or coordinate actions. Shared memory is fast but requires synchronization. Message passing uses pipes and sockets. Signals and remote procedure calls are also used. This chapter explores these communication techniques. Synchronization prevents race conditions in shared resources. Techniques include semaphores and mutexes. Monitors ensure mutual exclusion. Deadlock prevention is crucial using algorithms like the banker's algorithm. Understanding these ensures safe concurrent processing. Processes transition through states like new, ready, running, waiting, and terminated. State transitions are managed by OS schedulers. Examples include C groups and namespaces in Linux. Hyperthreading leverages CPU parallelism. This chapter explains these transitions and enhancements. Modern OS enhancements include hyperthreading and multi-core scheduling. Virtualization allows processes to run in virtual machines. These advancements improve efficiency and resource utilization. Understanding these helps in grasping modern OS capabilities. This chapter explores these innovations. A process is a program in execution, encompassing more than just code. It includes the program counter, registers, and memory contents. These elements are crucial for program execution. Understanding processes is foundational for OS management. This chapter delves into what makes a process. A process is an active entity, unlike a passive program stored on disk. It represents a program in execution and is managed by the operating system. Each process is assigned a unique process ID, PID, for identification and tracking. A process owns its memory space, which includes key segments, the text section, code, data section, global static variables, heap, dynamic memory, and stack, function calls and local variables. Process state changes such as ready, running, waiting, or terminated are crucial for proper scheduling and execution. This chapter covers these defining characteristics to help you understand how processes are created, managed, and executed in a modern operating system. Key components include program code, program counter, and stack. The data section stores global variables. The heap is for dynamic memory allocation. The process control block holds vital information. Understanding these components is essential for process management. The process control block, PCB, is crucial for managing active processes. It serves as the OS's data structure to track and control each process throughout its life cycle. It contains essential information such as the process ID, current state, for example, ready, running, waiting, and the program counter, which indicates the next instruction to execute. Additionally, the PCB stores CPU registers, memory management data, like base and limit registers or page tables, and I/O status information. The PCB supports context switching by saving and restoring the state of processes and plays a key role in scheduling decisions by providing all necessary process metadata. This chapter explores its importance in operating system management and how it enables multitasking, resource allocation, and process isolation. The PCB facilitates context switching by saving process states. It supports process scheduling decisions. Maintaining process isolation and control is crucial. The PCB aids in resource management and debugging. This chapter highlights its vital role in OS operations. Operating systems use PCBs to track and manage processes. Each process has a unique PCB with essential details. This includes process ID, state, and CPU registers. PCBs allow efficient scheduling and management. Understanding this representation is key to OS functionality. Processes transition through states like new, ready, and running. Context switching involves saving and loading process states. Scheduling algorithms determine process execution order. PCBs play a crucial role in these transitions. This chapter explores these key concepts. Operating systems manage process execution to ensure system stability and responsiveness. Their responsibilities include process scheduling, resource allocation, and security enforcement, ensuring that each process gets fair access to CPU time and system resources. Context switching allows smooth transitions between processes, while process isolation prevents one process from interfering with another, maintaining data integrity and security. These tasks are essential for enabling multitasking and maximizing resource efficiency in modern computing environments. This chapter analyzes these core responsibilities, highlighting how they support reliable and effective process management. Correct. OSs enforce access control to protect processes. Memory protection and user mode separation are key. Access control lists and capabilities are used. Process isolation maintains system integrity. This chapter covers these security measures. Processes communicate via pipes, message queues, and shared memory. These inter-process communication (IPC) methods enable data exchange and coordination between separate processes running concurrently. Synchronization uses tools like semaphores and mutexes to manage access to shared resources, preventing race conditions and ensuring data consistency. Multithreading enhances application performance by allowing multiple threads within a process to execute concurrently, sharing the same memory space while performing different tasks. These techniques are essential for efficient parallel processing and system responsiveness. This chapter explores their significance in the design and operation of modern operating systems. In conclusion, understanding process management and operating systems reveals how computers multitask efficiently. It sheds light on how the OS handles multiple programs, balancing performance and stability. Through mechanisms like process scheduling, context switching, and inter-process communication, operating systems ensure smooth execution and system reliability. This knowledge equips you to appreciate the complexity behind seamless computing and prepares you to engage more deeply with how modern systems operate. Thank you for watching this video.